You know, from the phone in your hand to a plane in the sky, pretty much everything is made by cutting metal. But have you ever wondered how we make sure that process is perfect every single time, all over the world? Well, it turns out there's a kind of secret language, an international standard called ISO 3685, and it makes all of it possible. I mean, think about it. If you're carving a massive block of steel with a tiny, super hard tool, that tool is also getting worn down. But how much wear is too much? Is it just a little dull? Is there a tiny chip in it? If we can't all agree on what worn out actually means, there's no way we can build anything reliably. And that right there is the fundamental problem this standard solves. So today, we're going to pull back the curtain on how this all works. We'll start with the unseen enemy, which is tool wear. Then we'll get into the common language we created to fight it. We'll decode the different faces of wear, see how we actually measure the damage, and finally, take a look at the future of monitoring this super critical process. All right, so let's start with the core conflict here, which is really at the heart of all manufacturing. The very act of creating something with incredible precision involves the slow, inevitable destruction of the tool that's doing the creating. It's a constant battle, all happening at a microscopic level. Right. So the goal isn't to stop wear entirely. I mean, that's literally impossible. The real goal is to understand it, predict it, and then manage it with extreme precision. Because when a tool fails unexpectedly, man, it can ruin expensive parts, cause huge delays, and even create some serious safety risks. So, how does the entire global manufacturing industry get on the same page about this? This is where our standard ISO 3685 comes in. You should think of it like the Rosetta Stone for toolware. It gives everyone a shared set of rules and definitions, so we're all speaking the exact same language. So what this standard really does is create a universal framework, specifically for these things called single-point cutting tools. Just picture the really precise tips on a lathe that carve away metal. Those are the workhorses of the industry. This standard means an engineer in Germany can look at data from a factory in Japan and know exactly what's happening to that tool. It basically standardizes the very definition of failure. Okay, so let's dive into this a bit. Now, what's so interesting here is that wear isn't just one simple thing. Nope. It's a whole collection of different phenomena, and ISO 3685 helps us classify every single one. It's kind of like a doctor diagnosing different specific illnesses instead of just saying a person is sick. The two main types engineers are always looking for are flank wear and crater wear. Flank wear, which gets the code VB, is that slow, gradual grinding down of the tool's side as it cuts. It's the most common, and usually the most reliable, indicator that a tool is getting close to the end of its life. Crater wear, on the other hand, is literally a scoop or a crater taken out of the top face of the tool. That's caused by the super hot metal chip sliding over it again and again. But what's actually causing all this damage? Well, deep down, there are four key things at play. You've got abrasive wear, which is basically like sandpaper, hard little bits in the metal scratching up the tool. Then there's adhesive wear. This is wild. It's when microscopic pieces of the material being cut actually weld themselves onto the tool and then break off, taking a tiny piece of the tool with them. And finally, you have diffusion and oxidation, which are basically chemical attacks happening at insane temperatures, where atoms are literally swapping places or the tool just rusts in a flash. So now that we know what to look for, how in the world do we actually measure it? This is where the standard gets super practical, guiding the actual tools and techniques we need to get to that microscopic level of precision. And get this, the scale of these measurements is just mind-blowing. ISO 3685 sets these incredibly specific thresholds. For a common carbide tool, the limit for that flank wear we talked about is often just 0.3 millimeters. To give you some perspective, that's about the thickness of 3 human hairs. That tiny margin is the difference between a perfect part and a piece of scrap. Broadly speaking, there are 2 ways to measure this. The classic way is called offline. You finish the job, you take the tool out, and you stick it under a super powerful microscope to see exactly what went down. The more modern approach is in process, using a whole bunch of sensors to listen, feel, and watch the tool while it's cutting, all in an attempt to predict failure before it even happens. So how does this whole in-process monitoring thing work? Well, it's pretty much a 3-step dance. First, you sense. You load up the machine with sensors for vibration, sound, force, you name it. Second, you process that fire hose of data. You use advanced algorithms to find those tiny, faint signals of wear that are hidden in all the noise. And finally, you predict. You use AI to analyze those patterns and forecast exactly when that tool is going to cross that critical wear threshold. And this predictive power, I mean, it is completely changing the game. We're moving away from just measuring past failures to actively preventing future ones. It's pushing us closer and closer to total manufacturing perfection. So what are these new smart systems made of? Well, at their heart, you've got artificial intelligence and machine learning. That's the biggest slice. But that AI needs fuel, and that's where sensor fusion comes in. It's combining data from vibration, sound, force, everything, all of which is cleaned up by advanced signal processing. It's not just one sensor. It's a whole symphony of data that creates a perfect picture of the tool's health. And the results? They're honestly staggering. Many of these AI-powered systems can now predict the remaining useful life of a tool with over 90% accuracy. Just think about that. That means fewer surprise failures, way less waste, and much higher quality parts, all because we can now basically see the future in the data. So the future isn't about choosing one method over the other. Not at all. It's about combining them. We use the real-time AI to predict a failure, and then we use those high-precision offline microscopes to validate the predictions and make the AI even smarter. This hybrid approach, all guided by the rules of ISO 3685, is how we guarantee the absolute best quality. So why does any of this really matter to you and me? Well, because this obsessive, microscopic attention to detail is what allows us to have things like flawlessly smooth phone casings, incredibly reliable jet engines, and life-saving medical implants that fit perfectly. This so-called secret language is really the foundation of quality in our modern world. And that leaves us with this final, really fascinating question. As our ability to predict wear gets closer and closer to perfection, what becomes possible? What incredible new things could we design and build if we could completely remove the fear of a tool ever failing unexpectedly? The possibilities there are truly limitless.